Okay, let's look at example number 14. So number 14 is a soil consolidation problem. Consolidation could be, the calculation could be a little on the trickier side compared with a lot of other geotechnical questions. But the thing is, after you really understand the process of consolidation, the calculation can be actually very, very straightforward. So again, try to pause the video for a couple of minutes, and so we'll be back in a little bit. Okay, so now we're back. Kind of continue our discussion about consolidation. That you can take a look at the reference manual, but again, man, the reference manual of all those equations, so they can be actually pretty it's not really user friendly in a sense if you look at all those three sets of equation over here. But I do enjoy this plot, and I'm probably gonna go over this plot a little bit later, and also introduce the way I would use for consolidation problems. So if you're interested, I have another video in my channel that was about 20-something minutes solving a consolidation problem that is not FE exam style, but more of the classroom textbook style. But if you can really understand all the in and out of that problem, then you shouldn't have any issues or any troubles of solving the FE problem. So I'm gonna ditch the reference manual for this one because again, not a big fan of the reference manual. So we have the normally consolidated clay, and basically we're talking about OCR is 1, the overall consolidation ratio is 1. We have the liquid limit is 45. And we know the average vertical effective stress is 2,000. So that is the current or the existing stress level that the soil is experiencing right now. And we have the placement of an embankment so that the vertical effective stress increased by 800 PSF. So now we're talking about 2,800 PSF. This is the total amount that the soil is experiencing right now. So asking for the void ratio decrease due to the placement of the embankment. So for any consolidation problem, it's really good to plot something like a E versus the sigma. Technically, it should be sigma prime again. So for a normally consolidated soil, then we're talking about a soil has never experienced a greater pressure in the geology history that is greater than the existing vertical effective stress. I know that's kind of a mouthful, but as long as you see the soil is normally consolidated, then the plot of E versus sigma prime is going to be a straight line, and the slope of the straight line is basically C sub C. Okay, so however much your horizontal is, time that C sub C, and you will get the change of the void ratio, which is delta E. Okay, so for this case over here, the stress increased from 2,000 to 2,000 plus 800. Okay. Oh, by the way, this is in log scale. Okay, so only in the log scale we can have this E versus sigma prime as a straight line. So basically, what we're talking about here is if you want to calculate delta E, that is the slope of this line, which is C sub C, the compression index, time log 2,800 minus log 2000. That's it. So actually, it's very, very simple, and all the log is 10 based, right? So, well, the question is, okay, for this particular problem, we don't really have the C sub C. We do have the liquid limit. So this is where we're going to use the empirical equation that you can find in the reference manual, that the relationship between the C sub C and LL is the C sub C equals 0.009 times LL minus 10. Again, this is an empirical equation. You would typically get C sub C and C sub S or C sub S or C sub R from a 1D consolidation test in the lab, but this happens to be the empirical equation from the reference manual. So, but based on that, our C sub C is 0.315. So you get that 0.315 inside, and time that log. Make sure you know the operation of the log, and the final answer is 0.046. So that is the change of the void ratio. So this problem is only asking for the change of the void ratio, the decrease of the void ratio. It's not asking specifically for the settlement, and but we do have the equation to convert the change of the void ratio to the settlement. But in that case, you have to know the thickness of the clay layer. But anyway, so that is this problem. So we're going to practice more in the next few examples.